Hello, we're going to look at the converse of Pythagorean theorem a little bit more than we did in chapter 2. So if we want to see if something forms a right triangle, if I can do 3 squared plus 4 squared, see how that relates to 5 squared, put a little question mark there. That's 9 plus 16 is 25, and that equals 25, so we know that's a right triangle. So let's look over here, 7 squared plus 24 squared. See how this relates to 26 squared. Well, we have 49 plus 24 squared is 576. And see how that relates to 26 squared, which is 676. Obviously, this is not, um, doesn't work, so we can say that this is not right. So this helps us to determine if it's right or not right. To get more specific, let's look at the relationship here. This is an obtuse triangle. If I have 7 squared plus 8 squared, see how that relates to 13 squared. Well, we have 49 plus 64. Is that greater than or less than 169? Hopefully you can see that this is less than 169, and it creates an obtuse triangle. Over here, if we take the two smaller sides, 4 squared plus 5 squared, see how that relates to 6 squared. 16 plus 25, that equals 41. That's more than 36, and that creates an acute triangle. It turns out this happens all the time with obtuse and acute triangles. So get you to the right slide here. This is the formula for telling if it is acute, right, or obtuse. Now we're going to talk real briefly about Pythagorean triples because they pop up a lot. And so it's good to have these memorized. There's a 3, 4, 5 triangle, a 5, 12, 13 triangle, a 7, 24, 25, 8, 15, 17, 9, 20, 40, 41. These triangles pop up a lot because they're times when Pythagorean theorem works out perfectly, and it's nice when things work out perfectly, right? So you'll see a lot. Now we can get multiples of these by taking each of the numbers and multiplying by the same scale factor. So this is also a Pythagorean triple. We call this a primitive and this a multiple, but uh, they both work. So from here on out, I think you can finish the rest of this.